Alright, we're going to look at a test 3 test review, and we're going to do this pretty quickly. So let's go and get into it. So the first few questions, we're looking at a uniform distribution. Okay, so where the amount of time a person waits is uniformly distributed 0 to 25 minutes. That means that our density function looks just like this. From 0 to 25, we have a rectangle whose area is 1, so that means it has a height of 1/25. Okay, so now question 1 says, what's the probability the person waits for more than 13 minutes? So here we're just saying 13 and up. What's that probability? Okay, so all we have to do then is multiply this length, which is going to be 25 minus 13, times the height. The height is 1/25. That's going to end up being 12/25, which is 48%. There we are. Okay, what's the probability a person waits between 10 and 12 minutes? All right, same deal. This time we're just going from 10 to 12. Okay, so that means that we have then a width of 12 minus 10, which is going to be 2 times 1/25. So we have 2/25, which is going to be the 0.08. All right, now part 3 says, what's the probability a person waits more than 10 minutes given that she has already waited for 5 minutes already? So now that means then we can't go from 0 to 25 anymore. We can only go from 5 to 25 because she's already waited 5 minutes. Okay, so that also means then that the height of my rectangle has changed because this rectangle is not length 25 anymore, it's length 20th, right? And remember, the area has to equal 1. So here we're asking now 10 or higher. So that's going to be a base length of 25 minus 10 for this rectangle times a height of 1/20th. So we get 15/20, or 75%. And so there we have it. I hope that makes sense. The only thing that's different about this is knowing that she's already waited 5 minutes changes my rectangle because 0 to 5 minutes is no longer possible. This is a conditional probability. All right, moving on to number 4, we're looking at an exponential distribution here with a mean of 7 years. Okay, so if you have a mean of 7 years, that means that our m value, or decay parameter, which is 1 over mu, is going to be 1/7. And here we're asking for the probability a computer part becomes defective in less than 5.6 years. So I'm going to write it like this. Probability x is less than 5.6. And according to our formula, that's going to be 1 minus e to the negative mx power. So that's going to be 1 minus e to the negative 5.6 divided by 7 power. Okay, now this is a calculator question, and you do want to practice this. And when you type it in, you should get 0.5507. So here, part A. I hope that makes sense. Just this is a formula you have to know here. This 1 minus e to the negative mx. And remember, m is always going to be 1 over mean. Alright, so let's get into the normal curve, which is what most of our test is about. And now I'm looking at 5. The test score from an elementary stats course are normally distributed with a mean of 72, standard deviation of 3.5. What test score has Z-score 1.6? So what we have to remember is the relationship between a value is always going to be the mean plus the Z-score times sigma, because Z-score stands for what? Number of standard deviations. Okay, so we always relate x to being that. So if x has a Z-score of 1.6, then all I have to do is plug in that number into this formula. We have 72 plus 1.6 times my standard deviation of 3.5. Again, this is a calculator situation, and you should get 77.6, which is what we meant here on part D. It's 77.6, not 0.1. All right, going on to number 6 now. This time we have the same mean and standard deviation. What is the Z-score of a test score of 67? So now, if you do the algebra on the relationship we have with x and solve for z, we end up with a Z-score. It always follows the pattern of x minus mu over sigma. So here we have that my test score was a 67, the mean is 72, and I'm dividing by 3.5. We're trying to see how many standard deviations away that is. It should be negative, and you should get about negative 1.43, which is part C. Okay, I hope this makes sense. All right, now let's pair that with probability. Okay, so now this time we have scores on a test that are normally distributed. We have a mean of 73, a standard deviation of 6. Alright, so you might want to say your test scores then were normally distributed, mean 73, standard deviation 6. That's the curve we're working with. What's the probability the student will score higher than a 76? Now, what I always recommend is to write this as a math statement, and it actually helps to get a picture here. So here's 73, here's 76, and I want to know this area. That's what probability is, area. Okay, now the way we do this is we need to get a z-score using the same formula. That's x minus the mean divided by the standard deviation. So I get a z-score here of 0.5. Okay, so that's my z-score. Now I take that z-score and I look it up in the table. So I have the table pulled up here, and my z-scores are running along this column on the left. And here I had a z-score of 0.5. So 0.50, that's at 0.19146. That's the area. Okay, so coming back to my curve, where does that show up on my curve? That number is 0 up. So that would be 0 up to that number. So this number here is a 0.19146. So the area I'm looking for is this blue part, not the gold. So how do I calculate what I wanted? Well, the blue and the gold together are 1/2. So if I say 1/2 minus 0.1946, that will give me the answer that I'm looking for, which is about 0.3085, which is part B. Now, we're going to repeat this over and over and over, okay? So what helps me, again, is to say the math statement here and draw the picture. That clarifies what I'm looking for. Okay, so for example, in 8, what's the probability a selected student score between a 76 and 85? Okay, so this time, here's 73, and I'm going from 76 to 85, and now I want this region in between, okay? Well, I just calculated the probability of 76 and up. I'm going to color 76 and up this blue, and we know that that area, which is what we just calculated in the other question, is the 0.0385. We've already done that part. Okay, but now I need to know what I'm really looking for is between 76 and 85. So how do I do that? Well, if I can calculate the 85 and up part, if I can calculate that, then I can subtract the two areas and get the answer I need. So let's do that. Let's get a z-score for 85. So 85, let's see, that was 85 minus the mean over standard deviation. That gives me a z-score of 2. Okay, so now I come look in my table again. At 2.0, I have a z-score of 0.47725. Okay, so that means here that where does that show up on the graph? That would be 0 all the way up to here. All that red region would be that 0.47725. So the gold region I'm looking for right here is again 0.5 minus what I just calculated, and that's going to be a small area of 0.0228. Okay, so that's the gold region. This is the blue region and the gold region together. So the region I'm looking for is the 0.085 minus 0.0228. And that should give me my answer. With my estimate, I got 0.2857, which will go with a 0.2858. Okay, and that's just from the decimal estimation somewhere, the difference there. I hope that makes sense. Now look, if you didn't draw the picture, this would be a very hard question to consider because we wouldn't recognize that I need to calculate two different areas and then subtract them. Yeah, and I didn't write this, and I should have, but the statement we were looking for is that we're going between 76 and 85. Okay, now let's do that on 9. So this time we want the probability that we get below a 67. So we want below a 67. Okay, so let's draw our picture. We have a mean of 73. This time we're looking at 67 here, and I want below. So I want all of this down here. Okay, now the problem is the chart only gives me from 0 up. So what do? Well, if that's the case, then what I'm going to do is I'm going to flip it around to some number on the other side and then calculate that value. And how do we do that? Just by flipping the z-score, and I'll show you what I mean. Alright, so let's get a z-score here. We have 67 minus our mean over 6. I get a z-score of -1. Okay, now my table doesn't have -1. I can look up +1 instead. So when we look up positive 1, I get the 0.3134. Where does that show up in my chart? That's this blue region here. So how do I get the gold region? Again, it's going to be the same thing. 0.5 minus the 0.34134. That will give me the gold region, which is actually the same as the gold region that I was looking for to begin with. Alright, now the reason that works, the reason I could look up positive 1 instead of negative 1, is because this chart is completely symmetrical, even though I didn't draw it symmetrically. If I flip it around, I get the same value either from the positive, below the negative side or above the positive side. We end up with the 0.1587. I hope these are making sense. If not, please let me know, okay? Let's do some more. Alright, so 10 through 13, we're basically doing the same thing. We have a normal distribution with a mean of 38 and a standard deviation of 2.75. Okay, now, drawing our pictures, or let's write our statements. And let's go ahead and write all of our statements here. So for 10, we want to know the probability that we're between 35 and 41, okay? For 11, we want to know of getting something greater than 38.5. For 12, we're looking for the 74th percentile. So what that means is x is less than k equals 0.74. That's a little different. We're looking for the opposite thing here. And in 13, we're looking for the 50th percentile. So probability of x is less than k equals 0.5. And that should be easy, actually. Number 13 is probably the easiest out of all of these. In fact, we can think about it right now. If you think about our normal curve here, we have a mean right in the middle of 38. That mean splits the curve into two equal areas. Each one has an area of 0.5. So what value is my 50th percentile? It is the 38. It's the mean. This will always be your mean. Will be the 50th percentile. Alright, so we got that one. Let's figure out the other three. Okay, so I know for 10 and 11, I'm going to need some z-scores here. Let's go ahead and calculate those z-scores. Let's actually draw our pictures first, and then we'll calculate our z-scores. So here I have a mean of 38. I'm going from 35 up to 41. And so I want this region here. Alright, for 11, I have a mean of 38, and I'm looking at 38.5, and I want above that. So those are the regions I'm looking for. Alright, now let's get some z-scores here. So the first one for 35, I have 35 minus 38 divided by 2.75. For 41, I'm going to do the same thing. 41 minus 38 over 2.75. And for question 11, I'm going to say 38.5 minus 38 all over 2.75, right? You see the pattern? We're doing the same thing. We're just changing out our x value each time. Alright, so now calculating our z-scores. And be careful when you do this. This is my second time doing it because I made some mistakes. For 35, I get negative 1.09. For 41, I get positive 1.09. And for the question for part 11, I get 0.18. Okay, now I'm going to look these numbers up in my chart. I can't look up the negative 1.09, so what would I do? Well, let's think about it for a little bit. If I looked up positive 1.09, I get this region. But what we're saying is, look, we want 1.9 standard deviations above and 1.9 standard deviations below. Those areas are going to actually be the same. So when I look up the 1.09 in my chart, I'll get the area on both sides of this curve that we're looking for. So let's look it up in our chart. 1.09, 0.36214. Alright, I wrote it over here, but that is that region. So when I double that, that will give me my 72% B. Great. Okay, now for 11, I look up 0.18 in my chart, and I get the 0.07142. Okay, now where does that show up? That would be this region here. That area is that 0.07142. So to get the area I want, which is the gold, I need to say 0.5 minus that value. And I'm going to get about 0.4286. And again, there's just some decimal error somewhere. We get D. Okay, that's the answer we're looking for. I hope these are making sense. Okay, practice using your table. Keep looking over it. All right. Now, 14, we want to draw a diagram representing a confidence interval. I did another video on this, but let me just do it really quickly. So we draw, let's get a better normal curve than that. Let's get something that looks a little bit more symmetrical. Still not great, but we'll just roll with it. Okay, so here's my sample mean. All right, we're going to mark out 2 spots. In the middle is my confidence level. That's the area over here in the middle. Now, we're going to mark out a distance going out to these intervals, and that distance is my error bound for the mean. How do you calculate an error bound for the mean? Well, you have to do that by calculating z alpha over 2, which is the number of standard deviations away I am, times the standard deviation itself. And then the area of the two tells is my significance level, and that's the alpha minus 2. Okay, now these two numbers that we're looking for are my x bar plus EBM and my x bar minus EBM. That is the idea of a confidence interval. You need to know this. You need to really know it, and not just memorize it. If it makes sense to you, these other questions are going to be pretty easy. All right, let's take a look. Okay, so we suppose scores are on a national exam are normally distributed. We don't know the population mean. We have standard deviation of 3 points. All right, we sample 85 scores, and it gives us a mean of 59. Find a 95% confidence interval of the exam. Okay, so first of all, what probability distribution do we need for this question? Well, I don't know the mean, but I'm testing 85 scores. If I have n greater than 30, then that tells me I'm going to use a normal distribution. If I had less than or equal to 30 and I don't know the population standard deviation, that means I need to go with a t-distribution. So because of that, I know that I'm going to go with a normal curve. So I know B and D are out. Now, which normal curve do I use? Okay, so we're actually going to follow a normal curve with mean mu and standard deviation sigma over root n. So when I calculate 3 divided by the square root of 85, I get this number here, part C. This is mu and sigma over root n. Okay, 17 says what's the value of z alpha over 2? Now how do I know that? Alright, so going back to this table here, what I'm saying is, in this question, what is that number there? And that tells me the number of standard deviations away I am. Alright, so we can look this up in the table, because what I know from here, if we have a 95% confidence interval, then I know that this region here, marked in red, is going to have an area of 0.475. How do I know that? Because that's 95% divided by 2. Okay, so I need to find the value in the table where I have 0.475 in the table itself. So let me look real quick. Where is 0.475? If you notice at 1.96, if you look at 1.96 in my table, I have exactly 0.475. That is the z-score that I need. So that's part C, and we just get that from our table. Now let's calculate our EBM. EBM is z alpha over 2 times that sigma over root n. We just calculated the z alpha over 2 to be 1.96, and we know that our sigma over root n is at 0.3254. So all I have to do is multiply those two things together, and we get a value of 0.6378. So there it is. Okay, now if you understand the table, this stuff is very, very simple. If you don't understand the table, or the picture, if you don't understand the picture, this is very difficult. It's confusing. But the picture really ties it all together. Okay, now 19. Which statement summarizes our confidence interval? So we want to say with 95% confidence interval, or with 95% confidence, true mean score in the exam, so all of them are the same so far. We're just changing the numbers here. What I need to do, look at my picture, I need to go plus the EBM minus the EBM. Okay, my mean was what? 59. My error bound is 0.6378. So if I look at my choices, look at this. 59 plus 0.6378 is right there. It's got to be A. That's the only logical choice. And so what I'm doing here is this is x bar minus EBM. This is x bar plus EBM. That's what I'm looking for. All right, now 20 through 21, we have this time a group of biologists. We have the acorns produced by oak trees. We test 15 trees. So notice that that is less than 30. That's a tip that we're going to probably have to use a t-distribution. All right, so now use a sample mean. They gave me a sample mean here and a sample standard deviation to construct a 95% confidence interval. All right, so now the way a t-distribution works is, well, it's the exact same, except that we're going to have to change the way we look up our t value. So here we're following a t-distribution with n minus 1 degrees of freedom. N was 15, so we have 14 degrees of freedom. Okay, and we also have a 95% confidence interval. So here we're looking at 95% confidence. Now on a t-distribution, we have to be careful with one thing. So that's 95% in the middle, which means we have 0.025 in each of these tails. Now my table asks for this value or less. So it's asking for all of that red region, and that would be the 0.95 plus the bottom tail, which gives me 0.975. So when I look up this value in my table, I need to look for where I have 14 degrees of freedom and I have 0.975 area below. Let me show you. That's the normal curve. Here's the t-curve. Okay, look, here are my degrees of freedom on the left. And see across the top we're looking at the 0.975 column, not the 0.95 column, 0.975. And we're looking down for 4 degrees of freedom. So we have a t value of the 2.145. That's my t-score. When I look at my choices, I don't even have a correct choice. None of these are right. The right answer is what we'll call E, 2.145. I'm sorry about that. We'll be more careful on the exam. So now how do I calculate my EBM? It's the same way. It's my t-score times the standard deviation, this time a sample standard deviation of root n. Okay, so that's going to be 2.145 times, let's see, my standard deviation was 130.72 divided by the square root of 15. All right, we're going to be very careful with plugging this in. And I get about 72.3975, which is, again, we don't have any of those correct choices because we didn't have the correct choice on the question before it. So we'll call this E here. I hope that makes sense. I'm sorry for the errors. All right, let's look at one more. 22 through 25. This time, we want to know the proportion of citizens of Mississippi who eat catfish. So we asked 600 Mississippians, 450 eat catfish. We want a 90% confidence interval. And this time we're testing proportion. Okay, so proportion is always going to follow a normal distribution. We're going to have a normal distribution with proportion there. And my standard deviation is going to be PQ over N, all in square root. Okay, so that means my proportion here was what? Well, I asked 600 people and 450 eat catfish. So here my proportion then is going to be the 0.75. All right, so I know that's either going to be B or C. And my standard deviation, that's my P prime, by the way, that's my sample proportion. To get my sample standard deviation, I need my Q prime here, which is 1 minus P prime, which is going to be 0.25. So my standard deviation is going to be the square root of 0.75 times 0.25 all over 600. And we take the square root of all that, and it should be very small. I get about 0.0177. So B is the distribution that I need to use. Okay, what's the value of my Z-score or T-score? We're going to use a Z-score here. I have a 90% confidence interval, which means when I have my table here, when I have my chart, I have 0.9 in the middle. I have 0.05 in each tail. All right, so this region then is going to have 0.45. So when I look in my table, you'll get the average between 1.64 and 1.65 to get 1.645. Okay, for a 90% confidence interval, you're always going to have that particular Z-score. Now to calculate EBP, it's the same thing that we've been doing. It's going to be my Z-score so the 1.645, times the standard deviation, which is the 0.0177, and we get this 0.0291. That's my EBP, error bound of the proportion, not the error bound of the mean. All right, now, which statement correctly summarizes my interval? So with 90% confidence, the true population proportion is between blank and blank. And we need to take that 0.75, which was our proportion, and we need to add and subtract this 2.9% to it. Okay, so if I add it, that's an easy calculation. I should get 0.7791. Notice part D is the only one with the correct answer there. That's the only one that's logical. And again, this is P prime minus my EVP, and this is P prime plus my EVP. All right, we did a lot of this in a pretty quick way. I hope this makes sense. Go over it until it does. This picture in particular is very, very useful. I think you'll see, though, that if you just try to memorize your way through this, it's going to be very, very hard. Learn the concepts. You have to know the concepts. I'll be happy to answer any questions you have. Good luck with your studying, and thanks for watching.